Welcome to Homework Lib.
Chapter 14, question 122. So I'm not going to read the entire question, but let's go one by one. They give us a reaction over here, CH4 plus Cl2, and reaction is very slow in the absence of light. With light, however, chlorine, with the presence of light, you get two chlorine radicals. So they don't show this as radicals over here, but what we normally see is chlorine with an electron. This single electron means that's a radical and is highly active. So once the chlorine atoms are generated, they can catalyze the reaction of CH4 and Cl2 according to the proposed mechanism. They're given two reactions 3 and 4, and CH4 is becoming a CH3 radical with the chlorine catching up one of the hydrogens, and CH3 radical is catching one of the chlorines and yielding a chlorine radical. So what happens is this chlorine radical then again goes into the reaction with CH4 and chlorine then again goes. So this is a typical catalyst where you see one of the molecules or atoms in this case in the reactants and in the end of the products so that can react again. The enthalpy changes and activation energies for these two reactions are tabulated as follows. By using the bond enthalpy for Cl2 in table 8.4, though I believe they want to say table 8.3 because 8.4 does not have anything with chlorine, determine the longest wavelength of light that is energetic enough to cause reaction to occur. So for this reaction 2 to occur, we need this light. And what we need to do is, if you can recall the formula, energy equals to H C over lambda. They're asking us the wavelength, lambda over here. So let's remember what they were. Energy is going to be in joules, and H is Planck's constant. That is 6.626 times 10 to the power of negative 34 joules second. C is going to be 3 times 10 to the power of 8 meters per seconds. And we need to find the lambda using these two values. And we also need the energy. So let's look at the energy for chlorine. It should be over here, 242. This is kilojoules per moles. So I'm going to adjust this as we want joules. So I'm going to multiply this by 1,000. And if you solve for lambda, what you're going to get is units of meters, but you want to convert that to nanometers with a conversion factor of 10 to the power of negative 9. So if you solve this equation over here, you're going to find lambda to be 494 nanometers. So that was A. And at B, using the data tabulated here, sketch a quantitative energy profile for the catalyzed reaction represented in 3 and 4. So we can do that, but let's make it a little bit more detailed by using the chapter, the C2 By using bond enthalpies, estimate where the reactants should be placed on your diagram. So let's just draw everything that is possible to be able to solve B and C together. Okay, there's a graph, and this is energy versus the reaction coordinate. So if I want to look at the energy for CH4, I want to look at the enthalpy for CH. This is 413. So if I multiply this number, let's solve it over here. 413 times 4. What we're going to get is 1652. So this is going to be energy of CH4. Now, what else do we need? We don't have the energy for chlorine because there's no bond. Over here, we have a CH3. So for CH3, 413 multiplied by 3. And then we're going to add Cl2, which is 242. This is going to be equal to 2039. These are in kilojoules per moles. So now we can draw these two of them easily. And let's write this was again for CH3 plus Cl2. So this first one is at a higher energy. So let's start it from here. And over here, you can see the overall enthalpy is going to be a positive value. So this is going to be endothermic. And energy of activation is 17. So let's say I start from here, go up 17, come down to a positive value. So what we start with is going to be 1652 plus 17, 1669. This value plus 4, 1656. Now this other value starts from lower and it goes up for 4 and comes down 109. So it starts with 1239, goes up to 1243, and comes down to 1130. Let's label them. The first one is going to be for reaction 1, CH4 plus Cl, and the second one is going to be for reaction, the second one, that's the fourth one, which is CH3 plus Cl2. Now, this is going to be the products for the reaction 3, so it's going to be CH3 plus HCl, and this guy is going to be CH3Cl plus Cl. Now, by using the bond enthalpies, estimate where the reactants should be placed on the diagram in part B, which we did. And did we do this? No, we did not do this yet. So we solved this for 3 and 4, but they want the reaction 1. So where can we place this reaction 1? So what we can think of is CH4 itself is 106, 152. And if we're looking for the Cl2, then we need to add 242 to this number. So it will start somewhere up here. And the value for that is going to be, if we add these two, we get 224, 549, 6 plus 2, 8, and 1. So it's going to start from the value, which is CH4 plus Cl2. This value is going to be 100, well, 1894. Okay. Use this result to estimate the value of energy of activation. So what I can come up with is the energy of activation for the first one is 4, and the second one is 17. Now, if you look at these two reactions, once you add them up, this CH3 is going to cancel with this CH3, and this Cl is going to cancel with this Cl. So we're going to get CH4 plus Cl2. So we're adding them up. That's why I would like to add the energy of activations up too. So the energy of activation is going to go up a plus 17 plus 4, which is 21. So 21 plus 1894 is going to be 1900. Help me with, please help me with the math, people. Um, 15. So this is going to be 1915. A lot of math is involved in this question. So we get this part C2, hopefully, if there's nothing else asked. Yes. So the species Cl and CH3 in reaction 3 and 4 are radicals. Draw a loose structure for CH3 and verify that that's a radical. So carbon has 4 electrons at the outer shell, and hydrogen has 1 electron. So if I'm going to add hydrogen and carbon, but I have 3 of the hydrogens and 1 carbon, so what I have is going to be, if I add these up, 4 plus 3, 7 electrons at all. So I'm going to draw carbon, hydrogen, hydrogen, hydrogen. I cannot put more electrons on hydrogen because it can only get 2 electrons at the around of this little circle. So I'm just going to add the rest of the electrons around the carbon. So what do we have? 2, 2, 2, 6 electrons already used. We have 7 electrons total, so there's 1 electron over here. This is a radical. This means this is a highly reactive 1 electron that wants to attack to any molecule. And if you do the same for chlorine, now chlorine has, we're just talking about 1 chlorine atom over here. So 1 chlorine atom has 7 electrons at the outer shell. So if I assign the electrons 2, 2, 2, 1, that's also a radical. At the last part, they're telling us this 3 and 4 is a radical chain mechanism. The reason for what we call this a chain reaction is at the end we have a chlorine that's a radical, and it goes back up to CH4. It attacks to, let's say there's a CH4, and it looks like something like this. There's also a bond. This chlorine is attacking to this bond over here and breaking that bond and making a bond with hydrogen. So it gives us a HCl. So that's why this is a chain reaction. It gets out, goes back in, gets out, goes back in. And how can we terminate this chain reaction? That would be actually simple. If this chlorine radical over here meets any other radical, like a CH3, making a bond here, this would give us CH3Cl. If this chlorine meets another chlorine radical, that's going to give us a Cl2. And these are going to be terminated. They're no longer as reactive as Cl radical or CH3 radical.